So welcome to Unit 1 of Advanced Higher Chemistry. What we're going to focus on today is understanding electromagnetic radiation and how to calculate the energy associated with electromagnetic radiation. So we'll basically start with an introduction to what electromagnetic radiation is. Now, electromagnetic radiation basically encompasses all the types of radiation that we can get from the sun, essentially. The main one of those is visible light. Visible light sits in the middle of the spectrum, but it encompasses a whole host of things. So radio waves are one. We have microwaves. We also have infrared, which I'll just write in red. Infrared. We then have ultraviolet. Ultraviolet. We then have X-rays and gamma rays. So all of these are types of electromagnetic radiation. And as we move across, we know that gamma rays and X-rays are particularly harmful to our bodies. UV light can also cause damage, but that to our bodies, these ones are usually benign, don't have a bad effect. And we'll find out why the ones at this end tend to be more dangerous. Now, because these are all types of electromagnetic radiation, they're all waves, which means that we can draw them or represent them as one of these, what we would call an oscillating wave. It goes up and down, it keeps going. But not all these waves are the same. There's something that makes them different from one another. So I'm going to draw one wave, but it's going to represent going from a radio wave the whole way to a gamma wave. So if we start here, should all be the same height, but what we notice is that the wavelength, which is the distance from one wave, so between here and here, or here and here, that is the wavelength. The wavelength. And the wavelength has a symbol. The symbol is that. Now, that is the lambda. So it's a Greek letter, lambda, for wavelength. And as we go across the spectrum, as we go from radio waves the whole way to gamma waves, the wavelength, it gets smaller. So as we go to gamma rays, we have the smallest wavelength. Radio waves has the biggest wavelength. And the wavelength determines essentially how long the wave is, and it also determines a lot of other properties. And wavelength is central. Now, the units of wavelength, we want units to always be in meters. For any calculation that you're going to do with electromagnetic radiation, you need to use meters. In chemistry, the main three forms of electromagnetic radiation that you're going to deal with are these ones. You're going to work infrared, visible, and UV. Now, the wavelengths in that region are often, so for infrared, visible, which we'll shorten to VIS, and ultraviolet, the wavelength is usually in nanometers. So we need to be able to convert meters to nanometers and nanometers into meters. Now, the relationship is that 1 meter, wrong way around, 1 nanometer is equal to 1 times 10 to the minus 9 meters. So that is 1 billion times smaller. So So if you're ever given a value in nanometers, to convert it into meters, you multiply by 10 to the minus 9. So if you've got a calculator, you'll be using the times 10 to the x button. So on my calculator here, if I'm wanting to put in 1 times 10 to the minus 9, I would put in 1, and then I've got this times 10 to the x, times 10, and then click the minus button, 9. And then that would be what I would do in order to convert whatever my number of nanometers is. So if it was 25 nanometers, I would do 1 times 10 to the minus 9, multiply by 25, equals, that tells me my number of meters. So this button here, the times 10 to the minus, times 10 to the x, is going to be used quite a lot. You've probably used that before, but just in case, that's showing you how it's used on my calculator here. So for these, if you're given a value in nanometers, you're going to have to convert it into meters. And the symbol for wavelength is lambda. Now that's one thing that is different for every type of electromagnetic radiation. The wavelength is different. However, they have one thing that is constant. And all EM, so that's electromagnetic radiation, all EM radiation travels at the same speed. So it travels at the same speed, or you could say velocity if you wanted to be a physicist rather than a chemist. Now I say it travels at the same speed, and that speed is c. So, E equals mc squared, Einstein's equation. C is the speed of light. Now c is on the back page of your data booklet. So c is here in that physical constants, and we're going to come back to this page quite a bit. The speed of light in a vacuum is c, and it is 3.00 times 10 to the 8 meters per second. So you don't need to remember it because it's written here, but you need to know that the speed of light in a vacuum, or specifically the speed of electromagnetic radiation in a vacuum, is c, and from the data booklet it's 3.00 times 10 to the 8 meters per second. And so if you have the wavelength and you have this, you can work out how far a wave is going to travel. So we've looked at wavelength and we have looked at speed. There is another property of electromagnetic radiation which relates those two things to one another. So that thing is the frequency. So frequency, which in chemistry the symbol we use for frequency is F. And the units are hertz. That's the non-scientific unit in chemistry. What we would really want to use is seconds to the minus 1. And what frequency is the number of waves that pass through a certain point per second. And the relationship between the speed and the wavelength is c equals f lambda. Now that equation is on page 4 of the data booklet. So we've got the data booklet here, page 4, right here, the small one, it's the first equation from advanced higher, c equals f lambda. So if you are given a lambda, you can work out the frequency, or if you are given the frequency, you can work out lambda. So normally what we would do is we would reorganize this equation. so that frequency equals c divided by lambda. So if you were told, for example, we know that c is a constant and lambda changes. So an example, if you were told that a wave has a wavelength of 450 nanometers, what is the frequency? Well, c is a constant, so we know that c equals f lambda. We know that c is always 3.00 times 10 to the minus 8, 10 to the 8, not minus 8, meters per second is equal to f multiplied by lambda. Now lambda is 450 nanometers, but we need it in meters, so we need to remember that 1 nanometer is 1 times 10 to the 9. So we multiply this by 10 to the minus 9 there. And so f is going to be 3.00 times 10 to the 8 divided by 450 times 10 to the minus 9. If we do that on our calculator, we get a quite high frequency of 6.67 times 10 to the 14 seconds to the minus 1. That's quite a high frequency for a wave. Yep, quite a high frequency for that wave. So we have that relationship. And this equation is in your data booklet, but it's going to be used a lot. Now, the next thing we need to discuss is a principle that can be quite difficult to get your head around, and it's called wave-particle duality. Now, wave-particle duality. And this is something that you will encounter in chemistry when talking about light and when talking about electrons. Now, when we talk about light, we usually think about light we know is a wave. We know it's a wave, so we know it can be represented by this, but light can act like a particle. So what we mean by acting like a particle, meaning it can collide with things, can impact with them in a way that we can imagine atoms combining with one another, colliding with one another, and having an effect. We can imagine light like that. So a particle we usually imagine like a dot. Now light and other things like electrons, we can sometimes think of them like waves, we can sometimes think of them like particles. That can be quite confusing. The way that I imagine it in my head is that this is going to be a crude gun. There we go, we've got a gun, and there's a bullet coming out of it. Now, the bullet is able to collide with things and will have an impact. Now the bullet, that's the particle aspect of it, but the path and the energy that were used for it to travel, that's the wave So if we can imagine every single beam of light, when it hits into things, that's like the bullet colliding with something and it's behaving like a particle. But the energy and the direction that it travels is all to do with the wave aspect of it. So it's a wave and a particle. It behaves in both ways. And what we call a particle of light is called a photon. So a particle of light is called a photon. And if we're talking about a photon, we are talking about one beam of light. So one wave or one particle. When you've got a light source, you're going to have lots of photons. But we are just talking about one of those. A single one. And in this analogy of the gun, when I talked about, well, the wave gives it the energy, it tells us how much energy. We can calculate the energy. So the energy of a photon is equal to h f. So the frequency of a wave is what determines the energy. But we know that C equals F lambda. So F equals C over lambda. It means we can also write this. E equals H C divided by lambda. That gives us the energy. Now I haven't addressed what this H is. This H. H is a constant, and it's called Planck's constant. Now Planck was a very, very, very famous scientist, and there are lots of institutions around the world called Max Planck Institutes, which are named after him, because he's very famous. And one of the things he did was develop this constant for being able to calculate the energy of waves. And Planck's constant, luckily for you, you don't need to remember it, it's in the data booklet, but Planck's constant is equal to 6.63 times 10 to the minus 34, so very, very small number, joule seconds. So joule seconds. And just to show you, it definitely is on the data booklet. Here's the back page of the data booklet. So in the physical constant section, we had speed of light in a vacuum c. Just one above that is h, 6.63 times 10 to the minus 34. Now, we're just going to do an example, calculating the energy. So we remember E equals H F, or E equals H C over lambda. It depends what you're given. Probably you're more likely to be given the wavelength. So that's the example we'll do. So we'll say a wave has lambda, we'll use the same one as before, 450 nanometers. What is the energy of one photon? So we're going to use this equation. We're going to have to use that equation because we have got lambda. Now we need to make sure that whenever we're doing something like this, all of our units agree. So energy, the units are joules or kilojoules. C is 3.00 times 10 to the 8 meters per second. Okay, so we've got meters. H is 6.63 times 10 to the minus 34 joule seconds. So we have got joule seconds, joules, meters, seconds, and then we've got wavelength. And our wavelength is 450 nanometers. And we've got nanometers, but we've got meters here. So we're going to need to convert that. So it's going to be 450 multiplied by 10 to the minus 9 meters. 450 times 10 to the minus 9 meters. So when we put these numbers in, energy is going to be equal to 6.63 times 10 to the minus 34. And I'm going to put in joule seconds just there, multiplied by 3.00 times 10 to the 8 meters per second, divided by 450 times 10 to the minus 9 meters. So I'm going to cancel out any units. So I've got meters and I've got meters. So they cancel out. I've got seconds, but on the same line I've got per second. So if they're on the same line, one's a minus, one's not a minus, they're going to cancel out. So the seconds cancel out, and that leaves me with joules, which is the right unit for energy, so I'm good. So all I need to do now is multiply out this equation. So using my calculator, what I would do is 6.63 times 10 to the minus 34 multiplied by 3.00 times 10 to the 8. Put that in brackets, divide by, and I'll just put it in brackets, 50 minus 9. You can do it all individual steps, or you can do it all together. And that, me, equals 4.42 times 10 to the minus 19 joules. That is hardly any energy at all per photon, which is what you would expect, because a photon is really nothing. It's one particle of light. But normally when we're dealing with the sun, we are talking about billions upon trillions upon quadrillions of photons all at once. And that gives us, so this does give us joules. However, this is chemistry. We do not like joules. That's not our standard unit. Whenever we do chemistry, the unit we want is kilojoules per mole. That's what we've worked out. Enthalpy before, kilojoules per mole. Ionization energy, kilojoules per mole. Everything. This is the unit we like for chemistry. And so we can modify this equation at the top in order that we can end up with a value in kilojoules per mole, which is something that we can relate to what we know in chemistry. So we're going to look at that equation next. Now the equation we use is going to be very similar. It is going to be energy. We're still going to use HF, but we're going to add in L here. And I'll talk about what L is. But if we are doing it here, energy equals hc over lambda, and again L. What is L? Well, L is Avogadro's number. It's a very big number this time. We've looked at quite small numbers before. And Avogadro's number, again, is on your data booklet in the back page. So where we had speed of light and we had Planck's constant, 2 up from that is Avogadro's constant. And it is equal to 6.02 times 10 to the 23 per mole. So the units, 6.02 times 10 to the 23 mole to the minus 1. Now, Avogadro's number, L, is the molar number. This 6.02 times 10 to the 23 is the number of atoms or molecules in 1 mole of a material. Now, Avogadro, he's the guy who worked this out, the scientist who worked it out. And what he discovered was that if you had 6.02 times 10 to the 23 atoms of carbon, it weighed exactly 12 grams. So it weighed exactly what the relative formula mass or relative atomic mass was for a given material. And he found out that if you had 6.02 times 10 to the 23 of any element, atoms of that element, it weighed the atomic number of that atom. And so this number is, whenever we talk about a mole, it's just this number of atoms or molecules, or for an ionic compound, formula units. So this is what turns what happens for one particle into a mole of particles. So for this equation here, HF was for 1 photon. Multiplying it by L gives us it per mole of photons. So it's not really any different. So what we'll do is we'll do the exact same thing, and we will do lambda again is 450 nanometers, which we know we have to turn into meters. 450 times 10 to the minus 9 meters. So whenever we do this calculation, energy is equal to 6.02 times 10 to the 23 mole to the minus 1 multiplied by H, 6.63 times 10 to the minus 34 joule seconds multiplied by 3.00 times 10 to the 8 meters per second. And all of that is divided by 450 nanometers, or 450 times 10 to the minus 9 meters. Now again, just to check that we're going to get units that are right, well, we've got meters here that we can cancel out, we've got meters here that we can cancel out. We've got second to the minus 1 and second on the same line, so they cancel out. And we've got joules and we've got per mole. So what we can do eventually, we'll get joules per mole and we can turn that into kilojoules per mole. When we multiply that top line out, we get a value, because that's constant, that's constant, that's constant. We get a value, 6.02, sorry, I'll just show you on the calculator. 6.02 times 10 to the 23 multiplied 6.63 times 10 to the minus 34 multiplied by 3.00 times 10 to the 8 equals that. So it's got an exact value, 0.1197378. So that equals 0.1197378 divided by 450 times 10 to the minus 9. So, divided by 450 times 10, sorry, I'm doing it on the calculator. So I just cut that number, divided by 450 times 10 to the minus 9 equals 266,084 joules per mole. Now, if that is that, we wanted our answer, we need to turn it into kilojoules per mole. 1 kilojoule equals 1,000 joules. So what we need to do is divide by 1,000, which gives us 266, if we're rounding up to the nearest whole number, kilojoules per mole of photons. Now this step here, dividing by 1,000, because this is in joules and we're always going to have to convert it into kilojoules, dividing by 1,000, you can either remember to do it here, or you can modify the equation at the top and remember to divide by 1,000 each time. It's up to you, because you either have to remember that you're going to have to turn joules into kilojoules by dividing by 1,000, or change the equation. It's up to you which one you remember. Now, the data booklet, the equation that it gives to you is E equals LHF. So it doesn't say anything about dividing by 1,000. It also doesn't give you LHC divided by lambda. It just gives you that. So again, it's up to you. LHF, to turn it into kilojoules, you're going to have to divide by 1,000. Or LHC over lambda, and again, divide by 1,000. It's up to you which equation you find better. This is the one here, given to you in the data booklet. That one is what's given to you in the data booklet. If you use that, your answer will be in joules per mole, and you'll need to divide by 1,000 to get it into kilojoules per mole. So you can either put the 1,000 in the equation at the start, divide by 1,000, or you can remember that this one gives you joules, divide by 1,000 later on. So just to review everything, what we looked at was electromagnetic radiation, and we saw that every type of electromagnetic radiation has its own wavelength, that all electromagnetic radiation travels at the same speed or velocity. That's a constant, 3 times 10 to the 8 meters per second, which is in the back of your data booklet. We then saw that we could relate the wavelength and the speed of an electromagnetic wave to the frequency. And frequency has units of s to the minus 1, and c equals f lambda. And again, that's given in the data booklet. We then looked at how to calculate the energy of one photon, E equals hf, and we looked at the reason for doing that is because of the wave-particle duality, that a wave has energy, but that the particle of wave is what has an impact, and so we need to be able to calculate the energy of a photon to find out what impact it might have. And we finished by looking at how we could work out in terms of the energy per mole, and that was by adding in this L, the Avogadro's number. So every single constant needed is on the back page of the data booklet. On the back page of the data booklet in the physical constant section, so the second table, you have C, you have H, Planck's constant, and you have L, Avogadro's constant or Avogadro's number, all in there for you to work with. The two equations that were used and can be modified to work out all the other ones are just in the middle of page 4 of the data booklet. C equals F lambda and E equals LHF. Avogadro's number multiplied by Planck's constant multiplied by the frequency. So everything we learned, all the equations are in the data booklet, as are all the physical constants. So that was electromagnetic radiation. Thank you for watching this video. I hope that clarifies what you need to know about electromagnetic radiation. Thank you for your attention.